Technology is reshaping the world faster than ever, and artificial intelligence for the Internet of Everything helps you make sense of it. We will focus on what it says about systems and data. Stay with me, the best part is near the end. Chapter 1: Intelligent Autonomous Things on the Battlefield. Introduction: The challenges of autonomous intelligence on the battlefield. AI will fight the cyber adversary. AI will perceive the complex world. AI enables embodied agents. Coordination requires AI. Humans in the ocean of things. Summary. Chapter 2: Policy Issues regarding implementations of cyber attack, resilience solutions. Introduction. Context: the need to address cybersecurity for physical systems. Cybersecurity role and certification of the operators of physical systems. Data curation. Market incentives. Conclusions and recommendations. Chapter 3: The Web of Smart Entities. Aspects of a Theory. Introduction. Smart Things: a vision of the next generation of the IoT, the use of artificial intelligence and the web of smart entities towards a theory of the web of smart entities interacting with automation. Depth of WSE. Conclusions. Chapter 4: The Value of Information and the Internet of Things. Introduction. The Internet of Things and Artificial Intelligence. Reworking Howard's initial example. Value discussion. Clairvoyance about C. Clairvoyance about L. Clairvoyance about C and L. Discussion. Conclusion. Chapter 5: Accessing Validity of Argumentation of Agents of the Internet. Introduction. Representing argumentative discourse. Detecting invalid argumentation patterns. Recognizing communicative discourse trees for argumentation. Assessing validity of extracted argument patterns via dialectical analysis. Intense arguments. Dataset evaluation of detection and validation of arguments. Conclusions. Chapter 6: Distributed Autonomous Energy Organizations, Next Generation Blockchain. Introduction to Distributed Autonomous Energy Organizations. Distributed Energy Supply Chain. AI blockchain to secure your energy supply chain. Potential blockchain business and implementation challenges. Roadmap for when to use blockchain in the energy sector. The evolution of public key infrastructure. Encryption. Why blockchain? Why DAEO. Overview of the AI-enabled blockchain and AI security opportunity. Conclusion in future research. Chapter 7: Compositional Models for Complex Systems. Introduction. Characteristics of complex systems. System design is a recursive process. Inductive data types and algebraic structures. Coalgebra and infinite data types. Operads as compositional architectures for learning. Conclusion. Disclaimer. Chapter 8: Systems and Research. Naval Research Laboratory, Washington, D.C., United States. Distributed Autonomous Systems Group, Code 5514, Navy Center for Applied Research in Artificial Intelligence, U. Naval Research Laboratory, Washington, D.C., United States. Battlefield Information Processing Branch, Computational Information Sciences Directorate, Army Research Laboratory, Adelphi, Maryland, United States. At our AAI 2016 Symposium on the Internet of Everything, IOE, one from an artificial intelligence, AI, perspective, we had participants who discussed the meaning, value, and effect that the Internet of Things, IoT, has and will have in ordinary life, on the battlefield. Internet of Battlefield Things, IoBT, in the medical field. Internet of Medical Things, IOMT, and other fields, and with intelligent agent feedback in the form of constructive and destructive interference, interdependence. Many of the invited and regular speakers at our symposium have revised and expanded their papers for this book. Other researchers who were not formally a part of the symposium also provided chapters. At the symposium, and for this book, we purposely left the topic open-ended. We were then, and are now, interested in research with an AI perspective that addressed how the IoE affects sensing, perception, cognition, and behavior, or causal relations, whether the context for an interaction was clear or uncertain. For mundane decisions, complex decisions on the battlefield, life and death decisions in the medical arena, or decisions affected by intelligent agents and machines. We were especially interested in theoretical perspectives for how these things may affect individuals, teams, and society, and in turn how they may affect these things. We were especially interested in what may happen when these things begin to think. Gershenfeld, 1999. Our ultimate goal was, and remains, to use AI to advance autonomy and autonomic characteristics to improve the performance of individual agents and hybrid teams of humans, machines, and robots for the betterment of society. In the introduction that follows, we review the background along with an overview of IOE. Afterwards, we introduce the chapters that follow in order of where they are listed in the table of contents. From Chambers, 2014, IOE connects people, data, process, and things. It is revolutionizing the way we do business, transforming communication, job creation, education, and healthcare across the globe. By 2020, more than 5 billion people will be connected, not to mention 50 billion things. With IOE, people get better access to education, healthcare, and other opportunities to improve their lives and have better experiences. Governments can improve how they serve their citizens, and businesses can use the information they get from all these new connections to make better decisions, be more productive, and innovate faster. From a recent view of IOE, IoT is all about connecting objects to the network and enabling them to collect and share data. Monroe, 2017. With the approach of IoT in everyday life, Geiger and Yang, 2013, on Battlefield's Internet of Battlefield Things, IoBT, in the medical arena Internet of Medical Things, IoNT, distributed with sensory networks and cyber-physical systems, and even with device-level intelligence Internet of Intelligent Things, IoE, comes a number of issues identified by Moskowitz, 2017, which are the explosion of data, cross-compatible systems, storage locations, security challenges, adversarial resilience, data exfiltration, covert channels, enterprise protection, privacy, and self and autonomic behaviors, and the risks to users, teams, enterprises, and institutions. As presently conceived, humans will often be the integral parts of the IoT system. Stankovich, 2014, p. For IOE, IOD, IOBT, IOND, IOI, and so on, will manifest as heterogeneous and potentially self-organizing complex systems that define human processes, requiring interoperability, just-in-time, JIT, human interactions, and the orchestration of local adaptation functionalities as these things attempt to achieve human objectives and goals. Suri et al. IOE is already impacting industry. 2. The Industrial Internet of Things, IIoT. Presently, there are numerous practical considerations. Whatever the systems used for the benefits afforded, each one must be robust to interruption and failure, and resilient to every possible perturbation from wear and tear in daily use. For system-wide failures, a system must have manual control backups, user-friendly methods for joining and leaving networks, autonomous updates and backups, and autonomous hardware updates. The list is similar to reordering inventory or goods automatically after a sale event or in anticipation of scheduled events by a large retailer like Amazon, Walmart, or Target. A system must also provide forensic evidence in the event of mishaps, not only with onboard backups, but also with automatic backups to the cloud. For new and future systems, there are several other questions that must be addressed. Will systems communicate with each other or be independent actors? Will humans always need to be in the loop? Will systems communicate only with human users, or also with robot and machine users? For future systems, we are also interested in what may happen when these things begin to think. Foreseeing something like the arrival of the IOE, Gershenfeld, 1999, pages 8-10. The former director of the MIT Media Lab, 3 predicted that when a digital system has an identity, knowing something about our environment, and being able to communicate, we will need components that can work together and change to produce a digital evolution so that the digital world merges with the physical world. Gershenfeld helped us to link our AAAI symposium with our past symposia on using artificial intelligence, AI, to reduce human errors. Intelligence is perceived to be a critical factor in overcoming barriers in order to direct maximum entropy production, MEP, to solve difficult problems. Martyashev, 2013, Wisner, Gross and Freer, 2013. But intelligence may also save lives. For example, a fighter plane can already take control and save itself if its fighter pilot loses consciousness during a high-G maneuver. We had proposed in 2016 that with existing technology, the passengers aboard Germanwings Flight 9525 might have been saved had the airliner safely secured itself by isolating the co-pilot who committed murder and suicide to kill all aboard. Lawless, 2016. Similarly, when the Amtrak train derailed in 2015 from the loss of awareness of its head engineer, loss of life could have been avoided had the train taken control until it or its central authority could effect a safe termination. NTSB, 2016. Similarly, for the memory lapse experienced by the well-trained and experienced engineer who simply failed to heed the speed limit approaching a curve, killing 3 and injuring multiple others. NTSB, 2018. Gershenfeld's evolution may arrive when intelligent things and humans team together as part of a collective intelligence to solve problems and to save lives. Goldberg, 2017. But autonomy is turning out to be more difficult than expected based strictly on engineering principles alone. For driverless cars, see Niedermeyer, 2018. Researchers involved with the IOE must not only advance the present state of these things, but also address how they think that the science of collective intelligence may afford the next evolution of society. Introductions to the technical chapters. The first research chapter, Chapter 2, titled Uncertainty Quantification in the Internet of Battlefield Things, was authored by Brian Gillian V and Stephen Russell. The authors are scientists at the U. Army Research Laboratory in Adelphi, Maryland. Their focus in this chapter is on mixed technologies that must be fully integrated for maximum military effect in the field. Technologies built by different businesses at different times for different purposes must somehow become integrated to work seamlessly. Recently, the Army was successful in integrating multiple technologies for national defense. Friedberg, 2018. They begin their chapter by reviewing a wide range of advances in recent technologies for IoT. Not only for commercial applications, but also their present and future use in military applications that are now evolving into IOBT. From their perspective, the authors believe that IOBT must be capable of not only working with mixed commercial and military technologies, but also leveraging them for maximum effect and advantage against opponents in the field. These applications in the field present several operational challenges in tactical environments, which the authors review along with the proposed solutions that they offer. Unlike commercial applications, the IOBT challenges for the Army include limitations on bandwidth and interruptions in network connectivity, intermittent or specialized functionality, and network geographies that vary considerably over space and time. In contrast to IoT devices' common use in commercial and industrial systems, Army operational constraints make the use of the cloud impractical for IOBT systems today. However, while cloud use in the field is impractical now, the Army has significant success with an integrated mission command network. NLC 2018 is an encouraging sign and motivation for the research proposed by Gillian and his co-author. The authors also discuss how machine learning and AI are intrinsic and essential to IOBT for the decision-making problems that arise in underlying control, communication, and networking functions within the IOBT infrastructure, as well as higher-order IOBT applications such as surveillance and tracking. In this chapter they highlight the research challenges on the path towards providing quantitative intelligence services in IOBT networked infrastructures. Specifically, they focus on uncertainty quantification for machine learning and AI within IOBT, which is critically essential to provide accurate predictive output errors and precise solutions. They conclude that uncertainty quantification in IOBT workflows enables risk-aware decision-making and control for subsequent intelligence systems and/or humans within the information analytical pipeline. The authors propose potential solutions to address these challenges, machine learning, statistical learning, stochastic optimization, generalized linear models, inference, etc. What they hope is fertile ground to encourage more research for themselves and by others in the mathematical underpinnings of quantitative intelligence for IoT and resource-constrained tactical networks. The authors provide an excellent technical introduction to the IoT and its evolution into the IoBT for field use by the U.S. Army. The authors are working at the cutting edge of technological applications for use in the field under circumstances that combine uncertainty with widely varying conditions, and in a highly dynamic application space. Chapter 9: Active Inference in Multi-Agent Systems, Context-Driven Collaboration. Horowitz, a former cybersecurity commissioner for the Commonwealth of Virginia. Chapter 5 is titled Policy Issues Regarding Implementations of Cyber Attack. Resilience Solutions for Cyber-Physical Systems. He is primarily interested in the policy implications of cybersecurity, in building cybersecurity prototype and standards focused on achieving cyber attack resilience, and in the education of future cybersecurity engineers. From his perspective, IoT is dramatically increasing complexity in cities, with commerce, and in homes across the country. This complexity is increasing vulnerability to cyber threats. See Zakrzewski S. 2017, interview of John Carlin, the chairman of the Global Risk and Crisis Management Group at Morrison & Foerster LLP and a former Assistant Attorney General in the National Security Division of the U.S. Justice Department. To reduce these risks, resilient cyber-physical systems must be able to respond to different types of disturbances, errors, cyber attacks. He has written that risks to organization, system, and infrastructure security systems challenge existing policies, indicating that new ones must be crafted that reduce cyber risks instead of focusing on reaction to the damage caused by a cyber attack. The author argues that these new policies require responses that anticipate attacks yet are able to distinguish anomalies caused by human error from those driven by the malicious cyber attackers who intend to cause significant damage to infrastructure and even to human health and life, or hope to control systems to achieve these or other malevolent purposes. Stuxnet. He concludes that anticipatory resilience solutions for cyber-physical systems will require teams of government and commercial organizations to work together to address the consequences of cyber attacks, to detect them, and to defend against them. The author offers a long-term view of cybersecurity policies, operational standards, and the education of cybersecurity professionals, especially engineers. The overview of cybersecurity provided by this chapter lets the reader know how much more work needs to be done to make cybersecurity a profession with standards. Chapter 10: Meta-Agents, Using Multi-Agent Networks to Manage Dynamic Changes. References Babcock C. What's the greatest software ever written? Witness the definitive, irrefutable, immutable ranking of the most brilliant software programs ever hacked. Information Week. August 11th. From https://www.informationweek.com/what's the greatest software ever written/d/did/10466033. Chambers J. Are you ready for the Internet of Everything? World Economic Forum. January 15th. From https://www.withforum.org/agenda/2014/01/ Are you ready for the Internet of Everything/ Dutta a 4pn, Feimster N. A developer-friendly library for smart home IoT privacy-preserving traffic obfuscation. AR14. August 22nd. From https://args4.org/pdf/pdf. Friedberg Jr. New tests prove IBCS missile defense network does work, Northrop. There's a real capability that can be deployed as soon as the government says it can be, Northrop Grumman's Rob Jassy told me, possibly even in months. Breaking defense. August 15th. From https://breakingdefense.com/2018/08/ new tests prove IBCS missile defense network does work Northrop/ Gager W., Yang L. Exploring Covert Channel in Android Platform. In 2012 International Conference on Cybersecurity, 2013:173-177. DOI/cybersecurity. Gershenfeld N. When Things Start to Think. New York, Henry Holt and Company. Giatti, Ali M., Dow I. Aramani, Westerland T., Liljeberg P., et al. IoT-based continuous glucose monitoring system, a feasibility study. Procedia Computer Science. Gilder. Wealth and Poverty, a new edition for the 21st century. Washington, D.C., Regnery Publishing, 1981/2012. Goldberg K. The Robot-Human Alliance. Call it multiplicity, diverse groups of people and machines working together. Wall Street Journal. June 11th. From https://www.wallstreetjournal.com/articles/the Robot Human Alliance 14972135576. Jacobs B. Introduction to Coalgebra, Towards Mathematics of States and Observation, Cambridge Tracks in Theoretical Computer Science. Cambridge, UK, Cambridge University Press, 2016. King R. Dell bets $1 billion on Internet of Things. Computing giants seeking new avenues of growth amid a shift in corporate spending to the cloud. Wall Street Journal. October 10th. From https://www.wallstreetjournal.com/articles/Dell bets $1 billion on Internet of Things 15076476601. Kessler A. The Ghost in the Machine. New York, Penguin Books, 1967/1990. Lawless W. Preventing, Another, Lubitz, The Thermodynamics of Teams and Emotion. In, Atmanspaker H., Filk T., Pothosey, eds. Quantum Interactions. Switzerland, Springer International, 2016:207215. Martioshev L. Entropy Production, Old Misconceptions and New Breakthroughs. Entropy. McHale. Military AI/machine learning speeds decision-making and efficiency for warfighters. Military Embedded Systems. May 29th. From http://mil-embedded.com/articles/military learning speeds decision-making efficiency warfighters/ Moskowitz I. Personal Communication, May 23rd. Monroe K. How to Beat Security Threats to Internet of Things. May 23rd. From http://www.bbc.com/news/av/technology 3992612/how to beat security threats to Internet of Things. Niedermeyer E. Autonomy Review, Fast-Tracking a Driverless Car. A period of remarkable progress seems to be giving way to a host of challenges that can't be solved with engineering talent alone. Edward Niedermeyer reviews Autonomy by Lawrence D. Burns with Christopher Shulgin. Wall Street Journal. August 27. From https://www.wallstreetjournal.com/articles/autonomy review fast tracking a driverless car 1535412237. Integrated Air and Missile Defense Battle Command System extends hundreds of miles to enable the multi-domain battlespace. Northrop. August 15. From https://news. Northrop Grumman. com/news/releases/Northrop Grumman's Missile Defense Battle Manager shares integrated air picture over vast distances. Railroad accident report, derailment of Amtrak passenger train 188 Philadelphia, Pennsylvania May 12, 2015, National Transportation Safety Board, accident report NTSB/RR16/02PB 2016-103218. From https://www.ntsb. gov/investigations/accident reports/RAR1602. PDF. NTSB issues investigative update on Washington State Amtrak derailment. National Transportation Safety Board. January 25. From https://www.ntsb. gov/news/press releases/pages/Mr. 201800125. ASPX. Stankovich J. Research Directions for the Internet of Things. IEEE Internet of Things Journal. doi/JIOT. Suri N., Tortonisi M., Michaelis J., Bugelis P., Benincasa G., Russell S., et al. Analyzing the applicability of Internet of Things to the battlefield environment. In Military Communications and Information Systems, ICMSS, 2016 International Conference on Wisner Gross A., Freer C. Causal Entropic Forces. Physical Review Letters. Zakshevsky C. The Cybersecurity Risks from the Internet of Things. Former Justice Department official John Carlin says smarter devices bring increased risks, and the world isn't ready. Wall Street Journal. December 17. From https://www.wallstreetjournal.com/articles/the cybersecurity risks from the Internet of Things 1513652760. 1 https://www.aaai.org Symposia Spring/SSS18 Symposia. PHP #SS02. For example, from General Electric on IIoT, see https://goo.com/digital/blog/everything you need know about industrial Internet things. Kirshenfeld is presently the director, the Center for Bits and Atoms, MIT, Cambridge, Massachusetts, Gershet CBA. MIT. Edu. For example, CRAAI Symposium at Stanford in 2016 at http://www.aaai.org Library Symposia Spring/SS16-01. PHP. Corresponding author, Brian Jalayan. Civet Mail. Mail. Corresponding author, Alexander Cot 1. Civet Mail. Mail. Corresponding author, Georgi at Aptima. Com. Corresponding author, BH8E at Virginia. Edu. Corresponding author, Joseph Lyons. 6 at Us. AF. Male. Corresponding author, Wolosky at Rose-Hulman. Edu. Corresponding author, Alec Schuldiner at Autodesk. Com. Corresponding author, Ira Moskowitz at NRL. Navy. Male. Corresponding author, Chen Shuhong at Gmail. Com. Corresponding author, Boris Galitsky at Oracle. Com. Corresponding author, Michael Milria at PNNL. Government. Corresponding author, Spencer Briner at NIST. Government. To create reusable proofs, algebras provide a uniform language that generalize, for example, groups, rings, lattices and monoids. Coalgebras are duals used to represent classes and objects, and Opered's model properties of mathematical structures of compositional architectures such as commutativity and anti-commutativity. E. Jacobs, 2016. Corresponding author, Hesham Fawad at NRL. Navy. Male. Chapter 11, Algorithm and Data. Uncertainty Quantification in Internet of Battlefield Things. Brian Gillian, Stephen Russell, U.S. Army Research Laboratory, Adelphi, Maryland, United States. Internet of Things, IoT, technologies have made considerable recent advances in commercial applications, prompting new research on their use in military applications. The Internet of Battlefield Things, IOBT, is the military counterpart of IoT, which is capable of leveraging mixed commercial and military technologies. Machine learning and artificial intelligence are the fundamental algorithmic building blocks of IOBT to address the decision-making problems that arise in underlying control, communication, and networking within the IOBT infrastructure, in addition to the inevitable part of almost all military-specific applications developed over IOBT. Uncertainty quantification for machine learning and artificial intelligence within IOBT is critical to provide an accurate measure of error over the output in addition to precision of output. Such information on uncertainty quantification enables risk-aware decision-making and control for subsequent intelligence systems and/or humans within the IOBT pipeline. This chapter provides an overview of classical and modern statistical learning theory, and how numerical optimization can be used to solve the corresponding mathematical problems with an emphasis on uncertainty quantification. Internet of Battle Things, Intelligence Systems, Decision-Making Introduction. The battlefield of the future will comprise a vast array of heterogeneous computational capable sensors, actuators, devices, information sources, analytics, humans, and infrastructure, with varying intelligence, capabilities, and constraints on energy, power, computing, and communication resources. To maintain information dominance, the future army must far surpass the ability of future opposing forces, kinetic and non-kinetic alike, to ensure mission success and minimize risks. This vision can only be achieved if systems progress from a state of total dependence on human control to autonomous and, ultimately, autonomic behavior. A highly adaptive and autonomous future will depend upon foundational algorithms, theories, and methods that do not fully exist today. There are many challenges in ensuring that the delegated mission goals are accomplished regardless of the immediate availability of human presence in the control loop or the partial attrition of mission assets. During the past decade, there has been a tremendous growth in the field of machine learning, ML. Large datasets combined with complex algorithms, such as deep neural networks, have allowed for huge advances across a variety of disciplines. However, despite the success of these models, there has not been as much focus on uncertainty quantification, UQ, that is, quantifying a model's confidence in its predictions. In some situations, UQ may not be a huge priority, e.g., Netflix recommending movie titles. But in situations where the wrong prediction is a matter of life or death, UQ is crucial. For instance, if Army personnel in combat are using an ML algorithm to make decisions, it is vital to know how confident the given algorithm is in its predictions. Personnel may observe a data point in the field that is quite different from the data the algorithm was trained on, yet the algorithm will just supply a, likely poor, prediction, potentially resulting in a catastrophe. In this chapter, we first provide a background and motivation scenario in section. In section, we discuss how to be able to quantify and minimize the uncertainty with respect to training an ML algorithm. This leads us to the field of stochastic optimization, which is covered broadly in this section. In section, we discuss UQ and ML. Specifically, we study how to develop ways for a model to know what it doesn't know. In other words, we study how to enable the model to be especially cautious for data that is different from that on which it was trained. Section explores the recent emerging trends on adversarial learning, which is a new application of UQ and ML and Internet of Battlefield Things, IOBT, in an offensive and defensive capacity. Section concludes the chapter. Background in motivating IOBT scenario. In recent years, the Internet of Things, IoT, technologies have seen significant commercial adoption. For IoT technology, a key objective is to deliver intelligent services capable of performing both analytics and reasoning over data streams from heterogeneous device collections. In commercial settings, IoT data processing has commonly been handled through cloud-based services, managed through centralized servers and high-reliability network infrastructures. Recent advances in IoT technology have motivated the defense community to research IoT architecture development for tactical environments, advancing the development of the IOBT for use in C4ISR applications, Kott, Swamy, and West, 2016. Toward advancing IOBT adoption, differences in military versus commercial network infrastructures become an important consideration. For many commercial IoT architectures, cloud-based services are used to perform needed data processing, which rely upon both stable network coverage and connectivity. As observed in Zhang and Carter, 2015, IoT adoption in the tactical environment faces several technical challenges. 1. Limitations on tactical network connectivity and reliability, which impact the amount of data that can be obtained from IoT sensor collections in real time. 2. Limitations on interoperability between IoT infrastructure components, resulting in reduced infrastructure functionality. And 3. Availability of data analytics components accessible over tactical network connections, capable of real-time data ingest over potentially sparse IoT data collections. Challenges such as these limit the viability of cloud-based service usage in IOBT infrastructures. Hence, significant changes to existing commercial IoT architectures become necessary to ensure their applicability, particularly in the context of ML applications. To help illustrate these challenges, a motivating scenario is provided. Detecting vehicle-borne IEDs in urban environments as part of an ongoing counterinsurgency operation by coalition forces in the country of Aragon, focus is placed on monitoring of insurgent movements and activities. Vehicle-borne improvised explosive devices, VIDEs, have become more frequently used by insurgents in recent months, requiring methods for quick detection and interception. Recent intelligence reports have provided details on the physical appearance of IED-outfitted vehicles in the area. However, due to the time constraints in confirming detections of VIDEs, methods for autonomous detection become desirable. To support VBIED detection, an IOBT infrastructure has been deployed by coalition forces consisting of a mix of unattended ground sensors, UGSs, and unmanned aerial systems, UASs. In turn, supervised learning methods are employed over sensor data gathered from both sources. Recent intelligence has indicated that VIDEs may be used in a city square during the annual Aragonian Independence Festival. A local custom for this festival involves decoration of vehicles with varying articles, including flags and Christmas tree lighting. UAS drone is tasked with patrolling the airspace over one of the inbound roadways and recoding images of detected vehicles. However, due to the decorations present on many civilian vehicles, confidence in VBIED classification by the UAS is significantly reduced. To mitigate this, the drone flies along a 3-mile stretch of road for 10 minutes to gather new images of the decorated vehicles. In each case, the drone generates a classification of each vehicle as VBIED or not, each with a particular confidence value. For low confidence readings, the drone contacts a corresponding UGS to do the following: 1. Take a high-resolution image, and 2. Take readings for presence of explosives-related chemicals in the air nearby, where any detectable explosives confirms the vehicle is a VBIED. Since battery power for the UGS is limited, along with available network bandwidth, the UAS should only request UGS readings when especially necessary. Following receipt of data from a UGS, the UAS performs retraining of the classifier to improve the accuracy of future VBIED classification attempts. Over a short period, the UAS has gathered additional training data to support detection of BIEDs. Eventually, the drone passes over a 1-mile stretch of road lacking UGSs. At this point, the UAS must classify detected vehicles without UGS support. Diagram of drone flight over a roadway. This example scenario highlights several research issues specific to IOBT settings, as reflected in prior surveys. Suri et al., 2016, Zhang and Carter, 2015. A needed capability to quickly gather training data reflecting unforeseen learning/classification tasks. 2. A needed capability to incrementally learn over the stream of field-specific data. Increasing the accuracy of classifying BIEDs by learning over the stream of pictures of decorated cars collected over 10 minutes of flight time. And 3. Management of limited network bandwidth and connectivity between assets, between the UAS and UGS along the road, requiring selective asset use to obtain classifier-relevant data that increases the classifier knowledge. Each of these issues requires the selection of learning and classification methods appropriate to stream-based data sources. Prior research, Botto, 1998b, Botto and CUN, 2004, Vapnik, 2013, demonstrates the equivalence of learning from stream-based data in real time with learning from infinite samples. From this work it follows that statistical learning methods adept to large-scale data sources may be applicable for stream-based data. This chapter opens with a survey of classical and modern statistical learning theory, and how numerical optimization can be used to solve the resulting mathematical problems. The objective of this chapter is to encourage the IoT and ML research communities to revisit the underlying mathematical underpinnings of stream-based learning, as they apply to IOBT-based systems. Optimization in machine learning. Behind the scenes of any ML algorithm is an optimization problem. To maximize a likelihood or a posterior distribution, or minimize a loss function, one must rely on mathematical optimization. Of course, the optimization literature provides numerous algorithms including gradient descent, Newton's method, quasi-Newton methods, and nonlinear CG. In many applications, these methods have been widely used for some time with much success. However, the size of contemporary datasets as well as complex model structure make traditional optimization algorithms ill-suited for contemporary ML problems. For example, consider the standard gradient descent algorithm. When the objective function is strongly convex, the training uncertainty, or training error, f(xk, f(x), is proportional to nk, where n is the amount of training data and k is the number of iterations of the algorithm. Thus, the training uncertainty grows exponentially with the size of the data. For large datasets, gradient descent clearly becomes impractical. Stochastic gradient descent, SGD, on the other hand, has training uncertainty proportional to 1/k. Although this error decreases more slowly in terms of k, it is independent of the sample size, giving it a clear advantage in a modern settings. Moreover, in a stochastic optimization setting, SGD actually achieves the optimal complexity rate in terms of k. These two features, as well as SGD's simplicity, have allowed it to become the standard optimization algorithm for most large-scale ML problems, such as training neural nets. However, SGD is not without its drawbacks. In particular, it performs poorly for badly scaled problems, when the Hessian is ill-conditioned, and can have high variance with its step directions. While SGD's performance starts off particularly strong, its convergence to the optimum quickly slows. Although no stochastic algorithm can do better than SGD in terms of error uncertainty, in terms of k, there is certainly potential to improve the convergence rate up to a constant factor. With regard to uncertainty, we would like to achieve a sufficiently small error for our model as quickly as possible. In the next section, we discuss the formal stochastic optimization problem, the standard SGD algorithm, along with two popular variants of SGD. In section, we propose an avenue for the development of an SGD variant that seems especially promising and discuss avenues of research for UQ and model predictions. Optimization problem. The standard stochastic optimization problem is where expectation is taken with respect to the probability distribution of equals, x, y, the explanatory, and response variables. In ML, f, w is typically of the form, whereas some loss function, such as 2. Most optimization algorithms attempt to optimize what is called the sample path problem, the solution of which is often referred to as the empirical risk minimizer (ERM). This strategy attempts to solve an approximation to f, w, using a finite amount of training data. This is the problem that the bulk of ML algorithms attempt to minimize. A particular instance is maximum likelihood estimation, perhaps the most widely used estimation method among statisticians. For computer scientists, minimizing a loss function, such as 2 loss, without an explicit statistical model is more common. Although it may go without saying that minimizing is not the end goal. Ideally, we wish to minimize the true objective, f, w. For finite sample sizes, one runs into issues of overfitting to the sample problem. An adequate solution to the sample problem may not generalize well to future predictions, especially true for highly complex, over-parameterized models. Some ways of combating this problem include early stopping, regularization, and Bayesian methods. In a large data setting, however, we can work around this issue. Due to such large sample sizes, we have an essentially infinite amount of data. Additionally, we are often in an online setting where data are continuously incoming, and we would like our model to continuously learn from new data. In this case, we can model data as coming from an oracle that draws from the true probability distribution P. Such a scheme is fairly standard among the stochastic optimization community, but is more rare in ML. In this manner, we can optimize the true risk, 1, with respect to the objective function, f, w. Stochastic gradient descent algorithm shows a generic SGD algorithm to be used to solve 1. The direction of each iteration, g, xk, k, depends on the current iterate xk as well as a random draw IP. Algorithm generic SGD. The basic SGD algorithm sets in k equals 1, and computes the stochastic direction as. This is essentially the full gradient method only evaluated for one sample point. Using the standard full gradient method would require n-gradient evaluations every iteration, but the basic SGD algorithm only requires the evaluation of one. We briefly discuss an implementation for logistic regression. Example: logistic regression. To make this algorithm more concrete, consider the case of binary logistic regression. When the amount of data is manageable, a standard way, Hastie, Tibshirani, and Friedman, 2009, to find the optimal parameters is to apply Newton's method, since there is no closed-form solution, to the log likelihood for the model. However, when n is large, this quickly becomes unfeasible. Instead, we could use a simple SGD implementation. In this case, we set the stochastic direction to be a random gradient evaluated at k equals xk, yk, which is sampled from the oracle. The implemented algorithm is then algorithm basic SGD for logistic regression again. Note that for each iteration only a single training point is evaluated. On the other hand, the full gradient method would have to use the entire dataset for every iteration. SGD variance as mentioned in section, the basic SGD algorithm has some room for improvement. In this section we introduce two popular SGD variants, mini-batch SGD and SGD with momentum. Each variant gives a different yet useful way of improving upon the basic SGD algorithm. Mini-batch SGD. One of the major issues with SGD is that its search directions have high variance. Instead of moving downhill as intended, the algorithm may wander around randomly more than we would like. A natural idea is to use a larger sample size for the gradient estimates. The basic SGD uses a sample size of n equals 1, so it makes sense that we might wish to use more draws from the oracle to reduce the variance. Specifically, we would reduce the variance in gradient estimates by a factor of, where n is the batch size. The mini-batch algorithm is implemented as shown in algorithm. Algorithm mini-batch SGD. It is shown in Botto, Curtis, and Knoss et al., 2016, that under assumptions of smoothness and strong convexity, standard SGD, sample size n equals 1 with fixed, achieves an error rate of. This convergence rate has several assumption-dependent constants such as the Lipschitz constant L and strong convexity parameter C. However, the defining feature of that algorithm is the K1 term, which implies that the error decreases exponentially to the constant. Using mini-batch SGD, on the other hand, yields the following bound, thus the mini-batch algorithm converges at the same rate, but to a smaller error constant. This is certainly an improvement in terms of the error bound, but of course requires n1 more samples at each iteration than the standard SGD. Thus it is not entirely clear which algorithm is better. If one could perform mini-batch in parallel with little overhead cost, the resulting algorithm would achieve the described bound without the cost of sampling n draws sequentially. Otherwise, the trade-off is somewhat ambiguous. SGD with momentum. Another issue with standard SGD is that it does not take into account scaling of the parameter space, which would require second-order information. A particular situation where this is an issue is when the objective function has very narrow level curves. Here, a standard gradient descent method tends to zigzag back and forth, moving almost perpendicular to the optimum. A common solution in the deterministic case is to use gradient descent with momentum, which has a simple yet helpful addition to the descent step. The stochastic version is, where the last term is the momentum term. As the name implies, this algorithm is motivated by the physical idea of the inertia, for example, of a ball rolling down a hill. It might make sense to incorporate the previous step length this way into the next search direction. In this sense, the algorithm remembers all previous step distances, in the form of an exponentially decaying average. Momentum helps SGD avoid getting stuck in narrow valleys and is popular for training neural networks. Unfortunately, convergence for momentum is not as well understood. An upper bound for a convex, non-smooth objective is given by Yang, Lin, and Li, 2016, in the form of. Note here that the error is given in terms of the average of the iterate. For problems in this class, the optimal convergence rate is, which this algorithm achieves. Nesterov's accelerated gradient descent. Nesterov's accelerated gradient descent, NAGD, algorithm for deterministic settings has been shown to be optimal for a variety of problem assumptions. For example, in the case where the objective is smooth and strongly convex, NAGD achieves the lower complexity bound, unlike standard gradient descent, Nesterov, 2004. Currently, there has not been a lot of attention given to NAGD in the stochastic setting, though, see Yang et al. We would like to extend NAGD to several problem settings in a stochastic context. Additionally, we would like to incorporate adaptive sampling, using varying batch sizes, into a stochastic NAGD. Adaptive sampling has shown promise, yet has not received a lot of attention. The development of a more efficient SGD algorithm would reduce uncertainty in the training of ML models at a faster rate than current algorithms. This is especially important for online learning, where it is crucial that algorithms adapt efficiently to newly observed data in the field. Generalized linear models the first and simplest choice of estimator function classes. In this case, the estimator is a generalized linear model, GLM for some parameter vector, Nelder and Baker, 1972. In this case, optimizing the statistical loss is the stochastic convex optimization problem, stated as, observe that to optimize EQ, assuming a closed-form solution is unavailable, a gradient descent or Newton's method must be used, Boyd and Vanderberga, 2004. However, either method requires computing the gradient of, which requires infinitely many realizations, xn, yn, of the random pair, x, y, and thus has infinite complexity. This computational bottleneck has been resolved through the development of stochastic approximation, SA, methods, Botto, 1998a, Robbins and Monroe, 1951, which operate on subsets of data examples per step. The most common SA method is the SGD, which involves descending along the stochastic gradient W, WTXT, YT, rather than the true gradient at each step. Use of SGD, EQ, is prevalent due to its simplicity, ease of use, and the fact that it converges to the minimizer of EQ, almost certainly, and in expectation at a rate when L, W, is convex and is sublinearly when it is strongly convex. Efforts to improve the mean convergence rate through the use of Nesterov acceleration, Nemirovsky, Juditsky, Lon, and Shapiro, 2009, have also been developed, whose updates are given as, a plethora of tools have been proposed specifically to minimize the empirical risk, sample size n is finite, in the case of GLMs, which achieve even faster linear or superlinear convergence rates. These methods are either based on reducing the variance of the SA, data subsampling, error of the stochastic gradient, DeFazio, Bach, and Lacoste-Julien, 2014, Johnson and Zhang, 2013, Schmidt, Roux, and Bach, 2013, or by using approximate second order, Hessian, information, Goldfarb, 1970, Shano and Fua, 1976. This thread has culminated in the fact that quasi-Newton methods, Mokhtari, GRB's Balaban, and Ribeiro, 2016, outperform variance reduction methods, Hu, Pan, and Kwok, 2009, for finite sum minimization when n is large scale. For specifics on stochastic quasi-Newton updates, see Mokhtari and Ribeiro, 2015, and Bird, Hansen, Noce et al., and Singer, 2016. However, as the analysis that yields linear or superlinear learning rates breaks down, and the best one can hope for is Nesterov's rate, Nemirovsky et al. Learning feature representations for inference transformations of data domains have become widely used in the past decades, due to their ability to extract useful information from input signals as a precursor to solving statistical inference problems. For instance, if the signal dimension is very large, dimensionality reduction is of interest, which may be approached with principal component analysis, Jolliffe, 1986. If instead one would like to conduct multi-resolution analysis, wavelets, Mallet, 2008, may be more appropriate. These techniques, which also include a k-nearest neighbor, are known as unsupervised or signal representation learning, Murphy, 2012. Recently, methods based on learned representations, rather than those fixed a priori, have gained traction in pattern recognition, Elad and Aaron, 2006, Merrill, Elad, and Sapiro, 2008. A special case of data-driven representation learning is dictionary learning, Merrill, Bach, Ponce, Sapiro, and Zisserman, 2008, the focus of this section. Here we address finding a dictionary, signal encoding, that is well adapted to a specific inference task, Merrill, Bach, and Ponce, 2012. To do so, denote the coding as a feature representation of the signal xt with respect to some dictionary matrix. Typically, is chosen as the solution to a lasso regression or approximate solution to a zero-constrained problem that minimizes some criterion of distance between dt and x to incentivize codes to be sparse. Further, introduce the classifier that is used to predict target variable yt when given the signal encoding. The merit of the classifier is measured by the smooth loss function that captures how well the classifier w may predict yt when given the coding. Note that is computed using the dictionary. The task-driven dictionary learning problem is formulated as the joy. That is the heart of artificial intelligence for the Internet of Everything. If it helped, a quick subscribe keeps more summaries coming. So how do systems and data connect? That is exactly where we started. Go back to the top and watch it click into place.